So, good evening. I'm last, so I try to be quick. So I'm Moser. I'm CEO at CADS. I have a master's degree in software engineering, and I've been working for CADS for 13 years now. We're part of the CADS marketing group, and also lately I'm now a full-time father as well, so that also defines a lot of my time. Today, I want to talk about bone segmentation and statistical shape modeling. First, let's go into segmentation. So bone segmentation is really a cumbersome process if you have to do it manually, and often that's the case, especially for skulls and in the CMF world, where there's often a lot of artifacts in images. You have different modalities, different machines, different resolutions. You don't have any standardization typically if you have a wide range of customers. And so you also need a lot of medical knowledge to fill that gap of image information that's often there. And yeah, you also have an inter-observer bias, typically if you scale your operations. So there's a lot of problems with it, or challenges, and we do need it as a basis for planning. So there's no way around it really. So it's a very integral part actually of the workflow. And being a manual process, it needs some time. So typically, as a surgeon, you don't have the luxury to get the segmentation right away. You need to wait till there is some segmentation done by a manual person, and then we can start the planning. So that prolongs the whole planning step. Where are typical problem areas? So the orbital areas, they're very thin. So typically with threshold segmentation, you don't get good results, and then therefore have a lot of artifacts in their holes. You need to close them manually, sometimes draw freehand in there. So that's a big problem. Also the maxillary area is also very thin bone areas typically. And the condyle areas are often difficult to really get a nice segmentation out there, as well as the teeth. Depending on the indication, patients often have braces, which also cause a lot of artifacts actually, or they have some other metal in there that make imaging really hard. Or for cone beam CTs or DVTs, the modalities are also really bad. It's a noisy picture, so roots are not often really good to see in there, and therefore, all these difficulties add to the time that a person would need to manually actually segment the DICOM data. And the little dot in here is if you want the nerve canal as well. It's also often very difficult to see in some images, but important for mandible planning actually. So we went ahead and said, okay, how can we increase the whole process efficiency, make it faster, make it more reliable and standardized, and we built an AI model that would take a lot of different machine DICOMs, modalities, and we created like a standard gold model segmentation for the whole skull all the time. So it really has a segmentation for the whole skull, undependent on the indication actually. And we feeded that as a training data, created a pipeline for that, used a state-of-the-art AI model for that, and and then had some post-processing for normalizing basically the data, bringing it into the same coordinate system to get then a smooth segmentation automatically of some DICOM data. The whole process in runtime currently needs about 3 minutes to run. So it's really, really quick, not too resource hungry, although a normal laptop is not really suitable, I have to admit. So result-wise, so we use the DICE score to get some good metrics out. As you can see, the skull and mandible work really well actually for testing. Also teeth, what does not yet work really well, or the results were very distributed, is the nerve canal actually. So it's very fine and granular detail, and therefore there's a lot of missing spots often in there. So there's definitely room for improvement. And also what we call implants as a label is really like everything external in there. So there's a lot of variation in there, which also explains the distribution here. So that's braces, implants, cranial implants, tubes, well, whatever you can find in there. And you can find a lot in there. And the model tries to make sense of it, but it's a big variation you can actually stumble upon. Some examples of the results of the AI model. As you can see, also we get a lot of variation in the bony structures. So they have defects in a lot of cases, as you would expect, because otherwise you wouldn't do a CT in the first place. But it also makes it difficult for the AI model, because for the training set data, you would get a lot of different data sets, but not very similar ones. And the model is really, really robust, as I can say. So it really is capable of dealing with situations that it didn't really saw before in the training set. It tries to come around and make sense of it from a 3D geometric perspective. And therefore, yeah, the results look really, really good, I think. But as I said, there's still room for improvement. So these are some cases that didn't really work out perfectly, I would say. So we had some shields in there, also some cranial defects with already mesh implants in there. Or the last one has a lot of tubes and metal in there, and also a big fracture, which yeah is its own problem, I would say, for segmentation. So like really big fractures, they can get messy in segmentation as well. And there you would also, which might be a next step, you would also want maybe to really have each segment or fracture separate to be able to reconstruct the defect. Statistical shape modeling. So this is a different technique for different purposes, maybe. I don't see them in competition. They are complementary, I think. So you could use statistical shape modeling for product development, as we already heard, but you can also use it to reconstruct defects. So if you have a perfect segmentation of some patient, then if there's a defect, it could look different, will look different than the healthy patient, and typically you want to get from the defect to the healthy patient. But sometimes that's not as easy as you would think. So on the left side, we see a craniosynostosis case, and it's often not as simple to say, okay, this is like the target shape that I want to get to for my design. And their statistical shape modeling can definitely help. Also for points of interest, landmarks and stuff like that, statistical shape models help. We have defined landmarks. We know where we can apply any forces and stuff like that. So that's very helpful there as well. some example defects we already saw, where statistical shape modeling helps especially. So, for example, that the cranial defect is more than on one side. So typically, what you could do instead of using a statistical model is mirror, which is often done in design. But if you have bigger defects, you typically need some reference on how the overall shape should look like. And also for big fractures, you want to have a good target model, and a good mean shape model then helps already. So what did we build to get a good statistical model out of different anatomies? So this is really not often too anatomy dependent. So the pipeline is very generic, basically, but what you would do is segment a lot of bone data, create a database out of it, create then landmarks. You also need to landmark basically the whole database, and then create templates for it to then be able, if you get a new sample like the fracture here, to create then a best fitting target model out of your statistical database. And that's also the type of statistical model that we saw earlier, or that same use case where you would actually want a statistical model to create a best fit reference for your patient, but a healthy one, and not just the segmentation, basically. And then you can use it for reconstruction or FEE model. Another example is the craniosynostosis. It's maybe a special case, use case for the statistical shape modeling. So we use it for actually making a surface scan of children. Typically, you don't want to use CT data or CT scan on very young children, because there is a huge risk of cancer then later. So you want to spare them the radiation. And so the idea is to create a surface scan and then infer the statistical bone model underlying it. So you would have a superimposition of some skin thickness that you distribute over the head surface, and then have your statistical bone shape model superimposed into that position. And then you can take that as a planning basis, actually, to go forward for the surgery planning. Thanks a lot.